do this problem. You're going to rotate the region formed by these equations around the y-axis. So first, guys, you need to be able to draw these equations. Okay, so be very comfortable drawing the equations. I think I'll tell you more about which kind of equations you need to draw. But for sure, you need a line, a parabola, ln of x, e to the negative x, you should be comfortable with, sine x, cosine x, square root of x. Okay, all those you need to be comfortable with. Okay, y equals 1/2 x minus 1. What does this look like? What picture does it look like? Or what graph does it look like? Okay, a line. And what is the y-intercept? -1. What is the slope? 1/2. That means up 1 over 2. Okay, up 1 over 2. Okay, and you connect these points, and there's my line. Okay. The region formed by this graph, also by y equals 0. Y equals 0 is the x-axis, I believe. Okay, so that's y equals 0. This is y equals 1/2 x minus 1. You also need y equals 2. So y equals 2 is a little bit up here. So let me draw y equals 2. And you also need x equals 0, which is just the y-axis, x equals 0. Okay, go ahead and shade in your region, guys, because this is where students go wrong. They shade in the wrong region, and then they rotate the wrong region. Okay, so go ahead and shade in the correct region here. Ruchi and Katie, what are you guys doing? Okay, have you guys shaded in your region? Okay, you guys are forever in my recording. Okay, that's good. You shaded in the region. Now we're going to rotate it about what? Okay, I want to see if you can picture this. Okay, if you rotate this about the y-axis, what is the solid going to look like? Do you see it? A bowl, but with a cap on top, right? A lid on top.
Yes.
Kind of like a Reese's peanut butter cup, right? Okay, so I'm going to draw the 3D thing, but I just want to let you know, if you can draw and understand it, it really helps you to understand how we're doing the formulas. But if you can't, don't worry about it. Another good question would be, is this a dx problem or a dy problem? We're rotating about a vertical line, so it is actually a dy problem. So this is going to be a volume pi r squared dy. Okay. But another way we know that it's a dy problem, okay, is if I define what r is, okay, r goes from the axis of rotation, okay, through the region to the furthest point on the region. That's my r, okay, and this acts kind of like a Riemann sum bar, okay, and this Riemann bar, do you see, has a thickness of dy, and that's why I knew I was wrong when I put dx up. This is a dy problem because this is a dy rectangle. Okay?
Yeah.
Okay. So right here, guys, when we figure out what this r is, okay, we're going to pull it out, okay, and guys, is this y minus y or x minus x? It's y, x minus x. Very good. Okay, so that means everything needs to be in terms of x, okay? So what is the x on this side? What is the x on this side? We have it in terms of y. Are you comfortable changing it? Good. So x is 2y plus what? 2. What is the x on this side of the Riemann sum bar? 0. So guys, it's x minus x is right minus left. Okay, so this is going to be 2y plus 2 minus 0. Okay, and if you're good at picturing this, what we did yesterday is like you would draw like a bunch of Riemann sum bars in, right? Into this solid. If you can imagine this recessed peanut cup, okay? And if you pulled out one of the slivers, okay, do you agree that it would be a circle? Would that make sense? It's a circle. Like pull out, like make another sliver, okay? They'd all be circles, okay? And that's where this pi r squared comes from. Remember, the formula is actually the same formula, okay, as what you had on the volume of the cross-sectional areas. Okay, it just turns out that this cross-sectional area is a circle, and that's why this is the pi r squared. Okay, if the cross-sectional area was a triangle, then this would be the triangle formula. Does that make sense? If the cross-sectional area was a semicircle, okay, then you would have had pi d squared over 8 here instead of pi r squared. Okay, it's just the area of the cross section. All right, so I know what r is, so this volume now is going to be pi, I'm going to substitute the r, 2y plus 2 quantity squared dy. Okay, and then let's get our limits. All right, this is a dy problem, so I go look at my region, okay, and I've confused this by putting in this left side, okay, but we really just look at our highlighted region, or our highlighted region, and we say, what's the lowest y value? What's the lowest y value? 0. What's the highest y value? 2. And then that is our answer. Okay, that's our setup. We haven't practiced a lot doing this by hand, so let's go ahead and do this one by hand. Your next unit is going to be called Special Integration, and it's going to make you feel special, okay? Because you're going to do a lot of this by hand. So it's good to start reviewing now. For your test on Tuesday, you'll have a calculator, so you can actually enter in your calculator. But it's good to practice and be comfortable doing it by hand, because the next test has no calculator, okay? So pi, this is 0 to 2. This right here, a lot of students would say that this is 4y squared plus 4. That's not true. What am I missing here? The middle child. You guys good with that? How many of you guys are middle children here? Confess. Middle children. Have your parents ever forgotten you? Have they ever forgotten you, Walker? Well, that might not be because you're a middle child, but we're gonna say it was, okay? And so guys, if you know what it's like to be a middle child, okay, don't forget the middle term here. So this is gonna be 4y squared plus 8y plus 4 dy. You actually need to FOIL this. It's 2y plus 2 times 2y plus 2. All right, then I'm going to see that this is actually a buy one, get two free problem. What a deal. Okay, you thought you just got to do one problem, but you get to do 3, okay? So this is going to be v equals pi. I'm going to integrate 4y squared, so that's going to be 4y cubed over 3 plus 8y squared over 2 plus 4y from 0 to 2. Okay, when I'm done, I'll multiply everything by pi. When I plug in the 2, I'll get pi times, this is going to be 4 times 8, which is 32 over 3. When I plug in the 2 here, that's going to be 8 times 4, which is 32 over 2. I plug in the 2, I get 8. And that's going to go from, plug in the 2. Then I'm going to plug in the 0. If I plug in the 0, do you see I get 0 plus 0 plus 0? So that's going to be 0. And then I slap a minus sign between. That's the first fundamental theorem of calculus. Okay? Plug in the 2, plug in the 0, and then slap a minus sign between. And the pi is a scalar. You guys okay with that? So I pulled the scalar out, and I'll multiply it in at the end. Okay, so this is going to be, actually, 32 divided by 2, is that 16? Okay, so 16 plus 8 is 24, is that right? So I have 32 over 3 plus 24 pi. That's my answer. Let me get a common denominator here. 32 over 3 plus 3 times 24 is 72 over 3. So that's going to give me 104 over 3. And don't forget, though, the pi. So there is my answer. Okay? If you are doing this with the calculator, okay, I've asked you this before. What would you put in for pi? The button. Does that make sense? Please do not put in 3.14 or 3.14159. That becomes an estimate of an estimate at the end. Okay, so please make sure you use the button. But why not just put the exact number? This is the exact answer. Any questions on this problem? Could you do it yourself? Yeah? Okay, go ahead and pass up your warm-ups. And let's look at your homework. Please pull your homework out, guys. So e to the negative x is like this. Y equals 0 is here. X equals 0. X equals 1. All right. So then what you want to do is you want to rotate this about the x-axis. So we're going to take this shaded region. We're going to rotate it about the x-axis. And we can see when we rotate it about the x-axis, it's going to kind of look like a plateau on its side. Kind of. How do I make this 3D? Like, you just go like this or something? I don't know. I'm not very good at this. There you go. I don't know. Anyway. Okay, so it's going to look something like that. And what I want to do is figure out if it's a dx or dy problem. They actually kind of gave it away. But we're rotating about a horizontal line, so we know it's going to be a dx problem, so we go ahead and write the formula. It's the integral of pi r squared dx, okay? And all we have to do is find what the r is and plug it in. This r is from the axis of rotation through the region to the furthest point on the region, and that's going to be y minus y. So this y here is e to the negative x, so it's e to the negative x minus 0. Okay, so then I'm going to square that. So if I plug it in, I'll get v e to the negative x squared dx. And guys, what do you do if it's a power to a power? What do? You multiply them, right? So this is going to be e to the negative 2x dx. Actually, this is a good problem to do. What's the integral of e to the negative 2x? Remember, the integral of e to the u is e to the u plus c, right? So I'm going to make my u equal to negative 2x. So du is equal to, boy, I haven't done this in a long time, negative 2 du dx is equal to negative 2. So du is equal to negative 2 dx, okay? I have not done this in a long time. I need to solve for dx, so dx equals du over negative 2. So I'm going to plug this into this right here, and this is going to be my u. I plug in two things, right? I plug in my u, and I plug in my dx. All right, so then this is going to become the integral of e to the u times du over negative 2. And I'm going to pull the negative 2 or the negative 1/2 out to the front. Okay, so this just becomes e to the du. And I know from my pink sheet that the integral of e to the u is e to the u. So this integral is negative pi over 2 e to the u from, e to the u. Let's just do the integral first. Negative pi over 2 e to the u. And that's going to be negative pi over 2. My u is really negative 2x, right? So negative 2x. Okay? And so what I need to do is, though, I need to take this from, what are my x intervals here? My x limits here. This is an x problem. What's my lowest x value, guys? 0. What's my highest x value? 1. So this is going to be from 0 to 1. After I integrated, this is what I got. So I'm going to take this from 0 to 1. Okay? First you plug in the 1. Let me erase all of this. First you plug in the 1, so you get negative pi over 2 e to the negative 2. Then you plug in the 0, you get negative pi over 2 e to the 0, but e to the 0 is really what? 1. Okay? Then you slap a minus sign in between. So this answer is negative pi over 2, in a sense, e squared is on the bottom, plus pi over 2. Hopefully that's the answer. All right, you guys ready? dx on the left side, please. dy on the right side. Okay, we're going to do volume of washers. Okay. I'm going to give you an example 1 on the left, an example 2 on the right. We'll do a dx problem, we'll do a dy problem, and then I want to give you kind of a general example down the bottom of the left. So this is how you're going to divide up your paper. Remember, you have lots of extra room on the top too. So if you want to write on the top, you can do that. And you might want to write your formulas on the top. So the formulas for this, right here, let's go ahead and start. These are going to be your formulas. So FYI, you can go ahead and write it. On the left side, your formula is going to be pi integral. Now, instead of 1r, it's going to be r squared, big R squared minus little r squared dx. If it's a dx, you'll have x1 and x2. Okay. On the dy side, you'll have pi r, big R squared minus little r squared dy. And if it's a y, it's y1 and y2. Okay. If you could, I think this is helpful. If you could make a note that this is totally wrong, like make a note and put that, like cross it out. Because this is a mistake students make every year. Okay, every year I have at least 2 students on the test make this mistake. It's not r minus r quantity squared. Okay, it's r squared minus r squared. We'll talk about why in a second. Okay, when do you use the dx? You use the dx if you rotate around a horizontal line, just like before. And when do you use the dy? You use the dy when you rotate around a vertical line, just like before. Okay. whenever you rotate around a horizontal line, you're going to have to solve for y equals. Whenever you rotate around a vertical line, because you'll have a horizontal Riemann-Sum bar, you have to get the x equals. Okay, and let's go ahead and figure out what we're doing. Okay, yesterday we found the volume of an orange. Okay, today we're going to find the volume of an egg. Okay, but we don't want the yolk. Does that make sense? We only want the white part of the egg. Okay, and so how would we do that? Okay, and the way we would do that is we would, still find the volume of the entire egg. Okay, so still the whole thing. Okay, remember yesterday we cut slivers into it? So you would cut slivers in here too. Okay, and no matter what sliver you cut, think about it, no matter what sliver you cut, okay, it is a dx sliver, do you agree? And no matter what sliver you cut, if I pulled it out, what shape would it be? Think about it. It would be a circle. No matter what shape, what sliver you cut, it would be a circle. Okay, and so that's why our formula was the integral of a dx, that's a formula for volume, okay? But remember, every cross-sectional area that we pulled out was a circle. So this area is the area of a circle, okay? And the area of a circle would be pi r squared dx, okay? And that was a volume of just this white part. Now, it turns out that you really only need this here, this part here, to be your r. Does that make sense? So that's what we talked about. Well, if we made this into a function, and we called it f of x, and if we took the region, okay, and we highlighted the region, we would just rotate this region about the x-axis, and that would give us the same thing as what this formula would give us. It turns out they're the same, okay? But what we're going to do today is, I want the volume of this egg, but I don't want the yolk inside it, okay? And so if you think about what I'm going to do, if I subtract out the yolk, okay, let me see, what color should I draw the yolk? Okay, there's a yolk inside, okay? But I'm going to do the same thing. Isn't it really just subtracting out the volume of this yolk? Yes. And this right here is also, think about it, this right here is also a v equals pi r squared, right? But it's a different r, right? It's a little r rather than a big R, okay? So that's why our new formula is going to be v equals pi r squared minus r squared dx. It's really just these two volumes subtracted from each other and then kind of simplified, and that's our new formula, okay? Now this egg isn't a perfect example because our limits that we're going to be doing, our limits are going to be the same. This egg has different limits, okay? So it's not a perfect example, but it's a good illustration of what we're about to do, okay? So real quickly, let me just make sure you understand. Our little r is actually from the right here, from the axis of rotation. If you think about it, if you think about what we're doing, we're actually taking, let me see if I can highlight this. We're actually taking this region right here. I'll do it in pink. We're actually taking this region here. Let's see if this makes sense. We're actually taking this region here, and we're spinning it around. We're spinning around the x-axis, and we're getting the volume of this purple part, okay, that we're spinning around, okay? And so the big R is here, and the little r is right here, okay? And we're hollowing it out, if that makes sense, okay? So now, if I took a sliver here, if I took a dx sliver, if I cut this egg for the volume that I want, remember we're hollowing out the yolk. Did I say yolk? Okay, pull out the yolk, okay? If you hollow this out, if there's no yolk in there, if I hold this and I show it to you, what would the cross section be now? You see, it'd be hollowed out. And so that's why this is called a washer. So it would look like a washer because now we have a hole. Any sliver you put would have a hole. This actually, the reason it's not a perfect example because you actually don't have, you're going to have some problems here, okay? And so we're not going to work problems like that. Our limits are going to be the same. So let me show you this definition here to make sure you understand. Okay, you might want to write this on your foldable. Okay, the definition of the big R now, okay, is the same. It's from the axis of rotation through the region to the furthest point on the region. Okay, the R is the same. It's the same definition we had before. From the axis of rotation through the region to the furthest point of the region. But now we're going to subtract out the yolk. Okay, and to subtract that out, we have a little r. We're going to subtract out the little r squared. And that little r is a little bit different. It is from the axis of rotation, but you don't go through the region, okay? You go to the closest point on the region. You head towards the region, but you don't go through it. And you stop at the closest point on the region, and that's your little r. So let's talk about a problem, and we can see how this works. Okay, you guys ready? So let's look at your dx problem. Let's go ahead and sketch your dx problem, the top right. It should look something like this. Go ahead and draw it and shade in your region. Now we're going to rotate this about a horizontal line, but the horizontal line we're going to rotate it about is y equals 6. Okay. Yesterday when we rotated this about a horizontal line, we rotated about the x-axis. And do you see if you rotate about the x-axis, you get a cone? You can see that? And when I took slivers of the cone, they were all perfect discs. They're all circles when I pulled them out. Okay. But now we're rotating about y equals x and y equals 6. If I rotate this region about y equals 6, do you see there's a hollowed out part in it? Okay, there's a space in it. Okay, if you think about it, what it's going to look like, I have a picture here that might be helpful. Okay, you're going to rotate this thing like this. Is this not helpful? Okay, you're going to rotate this thing, and so if you think about what's happening, it's like a cylindrical block with the cone pulled out of it. Okay, that's the picture. Okay, so I need to tell you, if you can see this picture, then that's great, okay? Because it's a little bit abstract, okay? If you can see the picture, you'll really understand what we're doing, okay? If you can't see the picture, it's actually okay. You just need to memorize the formulas, because if you memorize the formulas, they're right also. Okay, so essentially what we're doing is we're taking this cylindrical block and we're pulling out this cone from it, and we're finding the volume that's left, okay? So let's go ahead and, oops, wrong problem. Let's go ahead and do this problem. Okay. So what we're going to do first is we're going to write the volume formula. Okay. The hard part is figuring out, is it a dx problem or a dy problem? On the area problems, you could decide. You decide if it's x or y, and you could do it either way. One way might be easier or harder. But on the volume problems, you cannot decide. The problem decides for you. Okay. Are we rotating about a horizontal line or a vertical line? Horizontal. So automatically, this is a dx problem. Okay, if we're a vertical line, it would be a dy problem. And actually, the way I do it is I say, okay, well, let's just define what capital R is. Capital R is, remember, from the axis of rotation. So just put a dot on the axis of rotation. You start from the axis of rotation, you go through the region. So you have to go towards the region and actually go through it to the furthest point on the graph, and that is your big R. Okay, and I pull this big R out, and I say, what is the length of that big R? Is it an x minus x problem, or is it a y minus y problem? Take a look at it. You see it's y minus y. So what I need is everything in y equals terms. So what's the y equals here at the top? 6. What's the y equals here at the bottom? 0. So what is this going to be? It's a y minus y. Well, that's weird. Wait, could that be right? Let me think. Okay, let me try to do another R. R is defined from the axis of rotation through the region to the furthest point on the graph. From the axis of rotation through the region to the furthest point on the graph. Is R always a constant number? Yes. So doesn't it make sense that it just turns out to be a number? It's just 6. Okay. So I'm going to rotate this first about this y equals 6 axis. And do you see if I rotate this big R about this thing, it's going to be about the y equals 6. It's going to turn out to be a big cylindrical block on its side. Okay. Then I'm going to rotate the little r and subtract it out. So let's think about this. What is the little r? The little r is from the axis of rotation. Go ahead and put a dot. Don't go through the region, okay, but go towards the region. So go towards the region but not through it. And then go to the closest point on the region. And that's your little r. Okay, that's your little r. So let's do another little r. The little r is from the axis of rotation. Don't go through the region. Go towards it, but don't go through it. Okay, go to the closest point on the region, and that's your little r. So do you see little r changes, whereas big R does not? Okay, and so let's pull out a little r. Let's pull it out. Guys, is this little r a y minus y problem or an x minus x problem? Y minus 1, okay? So what's the y value on top? Y equals 6. What's the y value on the bottom? 2x. So this little r is going to be 6 minus 2x. So guys, once you define this big R and little r, all you do is plug it into the equation. So that's going to be 36 minus the quantity, 6 minus 2x squared dx. Okay, you just plug it into the equation. And that's exactly how I'm going to grade. I'm going to say, hey, did you find big R? What did you say it was? Okay, did you find little r? What did you say it was? Okay, 2 points for that, 2 points for the little r. Did you put it into the integral correctly? Okay, great. Did you get the limits correct? That's another point. Does that make sense? And then did you get the final answer correct? That would be 1 point. All right, so this is a dx problem. So I go to the region that's highlighted. What's my smallest x value? 0. What's my biggest x value? 3. Okay, and there's the answer. You guys can put that in your calculator and figure that out, or you could do it by hand. Okay, but we're going to stop there here. All right, any questions about rotating about y equals 6? Let's go ahead and rotate about a vertical line now. So let's go to this problem here, and we're going to rotate about a vertical line. So go ahead and sketch your picture and shade it in. Okay, we're going to rotate about the y-axis, so I'm going to put a spin on the y-axis. Okay. Yesterday, when we did a problem like this, we rotated about x equals 3. So yesterday, we rotated about x equals 3 here. And do you see when you rotate about x equals 3, you get like a cone, right? And there was no hollowed out portion on that cone. Okay. But today, when you rotate this figure about the y-axis, do you see you get this big cylinder, but then the cone is hollowed out from it. Okay. Yeah, and that's why, thank you. That's why it's called a washer. I'll show you why it's called a washer in a second. But let's take a look at this. Okay, we need to decide for this volume, okay, r squared minus r squared. Is it a dx problem or a dy problem? Dy. We're rotating about a vertical line, so it's dy. Okay, but really the way I do it is I just draw my r. My r goes from the axis of rotation, okay, towards the region, go all the way through it. I'm finding my capital R to the furthest point on the region, and that's my capital R. And your R, guys, is like a Riemann sum bar. I mean, you could just think about it. R stands for Riemann sum. Not really. We could think about it that way, okay? And if this is a Riemann sum bar, doesn't it make sense that that would be a dy width, okay? So this should be a dy problem, which it is, okay? So here's my R from the axis of rotation through the region to the furthest point on the region. Let's do another big R. From the axis of rotation through the region to the furthest point on the region. Whoa, you know what's going to happen here? Can you even see it? It should be another constant. Do you see it? If you don't, it's all right. Okay, let's just go ahead and pull out this big R. Pull out this big R. Is it an x minus x or a y minus y? X minus x, all right? That means we need all the x equals. So what's the x equals on this side? X equals 3. What's the x equals on this side? 0. So this is going to be 3 minus 0. Guys, make sure you do right minus left, okay? Don't do left minus right. All right, so that's my big R. My little r is, let me pull out all these r's. There's a lot of them here. So, okay, let me do a little r. So the little r is from the axis of rotation. Don't go through the region, okay, and stop at the closest point on the region. There's my little r, okay? And you can see the little r is going to vary. All right, so let me pull out this little r. What is the length of this little r? Is it x minus x or y minus y? X minus x. What's the x on this right side going to be? Y over 2. Do you guys see it? See that? It is y equals 2x. but that's the exact same as x equals y over 2. So this is going to be y over 2 minus, what's the x on the left side of this little r? 0. It's going to be x equals 0. Okay, so that's y over 2 minus 0. And then, guys, once you get the big R and the little r, it really is just a plug-in. It's going to be v equals pi 9 minus y squared over 4 dy. Okay, this is a dy problem. Okay, so go look at your shaded region. What's my lowest y value? 0. What's my highest y value? 6. Okay, and there's your setup. I think the hardest thing students have trouble with now that we introduce washers is how do you know it's a washer and how do you know it's a disc? Okay, well, yesterday when we rotated not about this line, but we rotated about this line, right? If I asked you to find the big R, let me pull out these. So we're rotating about a different line now. Let's make sure we understand. If I asked you to, yesterday when I said find the big R, you said from the axis of rotation through the region to the furthest point, you said big R, right? Now, if you find a little r here, there won't be one. See if that makes sense. From the axis of rotation, don't go through the region. You're not allowed to go through the region, okay? And then go to the closest point in the region. Do you see the axis is flush? It's flush up against the region. And when your axis is flush up against a region, you'll have no little r, okay? But if there's a space, if there's a space between your axis and the region, that's where the little r comes from, okay? And if you can picture it, it helps you too. So you can see, if you can picture this, when we rotated this about the y-axis, you could see that you had this hollowed out space, okay? And if you think about this hollowed out space, if I took dy's slivers in here, because this space is hollowed out, if I poured out a sliver, do you see that it wouldn't be a disc? It wouldn't be a full circle. It would be like a washer. Does that make sense? It would be a circle, like a donut. And that's why this is called a washer problem and not a disc problem. Okay? And it really doesn't matter if you call it the right thing or not. It really just matters if you can calculate it. All right, I want to give you another example. I want you to put this example in this section right here, the bottom left section. So this is on the dx side. Okay? And I want you to draw this picture with me. Can you cross out what I wrote there? I wrote some stuff that's not relevant there. So what you have, don't worry about. I'm going to do this problem with you. I want you to draw just kind of a random function like this, and this will be called fx. And then I want you to draw another function like this, and this will be called g of x. Okay? And these are going to be the boundaries for a region, so go ahead and highlight this region. I made this a lot bigger than I meant to, so FYI. This is the region right here. And I want to rotate this kind of suspended region here about the line y equals -1. So there's a line down here. This line is y equals -1. So this blue here, this is the x-axis, and this is the y-axis. Okay? And FYI, this intersection here is going to be called x1, and this intersection here is going to be called x2. So I'm going to take this yellow shaded region, and I'm going to spin it and rotate it about y equals -1. Can you spatially see what that volume is going to look like? I'm going to find the volume. It's like a donut. You guys see it? Kind of like a donut or a wreath, okay? And I'm going to find that volume. Well, let's think about this. I am rotating about a horizontal line, okay? So the volume's a dx problem, okay? I might have a little r, I might not, but the generic formula is it's an r, r squared minus r squared. I'm rotating it, so it's going to be a pi r squared problem, not a triangular problem or a rectangular problem or whatever. So that's where I get the pi r squared. I need my big R, okay? Do you agree that my big R would be from the axis of rotation, go towards the region, through the region, to the furthest point on the graph, right? That's my big R. Let me figure out what the equation for this big R is. Okay, let me pull it out of the graph. Okay, if I pull it out, do you see it's y? Do you see it's y minus y? What's my top y going to be though? F of x. What's my bottom y going to be? So do you see that this is minus -1? What does minus negative 1 mean? That's going to be a positive. And students have a lot of trouble with this. And when I do it with you guys, it seems really logical, but for some reason when you go to homework and you go to your test, you have some trouble with this. Okay? So let's do the little r now. The little r is from the axis of rotation. Don't go through the region, but go towards it. Go towards the region. There is a hollowed out space here. Okay? And stop at the closest point on the region, and that's my little r. Okay? Pull little r out of your paper. Okay? Is it an x minus x or y minus y? Y minus y. So take the top y value. What's the top y value? G of x. Subtract the bottom y value. What's the bottom y value? Negative 1. And so do you see this turns positive also? Okay? So I have a big R, I have a little r. All you do is plug it right into your equations. V equals pi integral. Capital R, so f of x plus 1 quantity squared. Okay, fix that. Minus little r, which is g of x plus 1 quantity squared dx. And let me go ahead and get my limits. This is a dx problem. Go to my shaded region. What's the lowest x value on my shaded region? x1. What's the highest x value on my shaded region? x2. And that's your limit. Okay? This is very similar to how number 29 on your homework is going to be set up. Okay? Actually, I don't think it has this negative 1. But it's going to have a crisscross function here. But that one's also going to have a highlighted portion on this side, just to make it more fun. Okay? So what you'll do is you have two of these integrals added together. Okay, for your number 29. Do you want to set up 29 or set up as much as we can? Go ahead and pull out 29, your homework, guys. Your homework